Welcome back. Today we're talking about applications of least square solutions, material from 6.6. Let me just remind you all that what is a least square solution. So the least square solution of a system AX equals B is given by, solving the system ATA is my new coefficient matrix equals ATB is the kind of right-hand side. The solution that you get from this consistent system is going to be given by x hat. And I just like to think about this geometrically, as we discussed last time, that, the way I think about this is that, A is a matrix from, say, Rn to Rm. You've got the column space here in, say, Rm. And you've got a vector B. So if this is the column space of A sits inside Rm. And if you have a vector B, well, sometimes it's in the column space, in which case you have a consistent system, AX equals B. If B is not in the column space of A, then AX equals B is inconsistent. And what you do is you project B down to the column space, you get B hat. And then now you are consistent, so there is some x hat that gets sent to B hat, and that x hat that does that is your least square solution. So how are we going to apply this to a kind of real world setup? So here's the application that we want to talk about. Loosely speaking, what you want to think about here is that you're given data points. Let's say x1, y1, x2, y2, up through, x and yn. So these are points in the plane. And, so maybe this is the x-axis, the y-axis. So you're given a bunch of points in the plane. And, you want to think about this as, depending on your major, you can think about this as maybe time, and this is concentration of some, chemical that you're considering, or maybe temperature or something. If you're an economics person, this could be time, and this could be salaries or, wages or unemployment or something like that. Let's think employment, we're getting better. And then the idea is that what is the best line? What is the line that best fits this data? And, loosely speaking, hopefully we know what that means. It's the line that, I can't go through all these points because they don't sit on a line, but I want a line that, in some sense is closest to all those. We'll talk later what I actually mean. It turns out we're going to minimize these little vertical distances to the line. But the idea is that if we're assuming that they actually lie on a line, then we know what a line is, right? We know that y equals beta naught plus beta 1x. This is going to be the line that I'm going for. And this gives rise to a system. Let me actually go to the next page here. So if I'm given these data points, x1 through, x1, y1 through x and yn, then I get a system out of this that's going to look like, beta naught plus beta 1 x1 equals y1, beta naught plus beta 1 x2 equals y2, dot, dot, dot. For every point, I get an equation. And what do I have here? Well, this is a system, right? So remember, the x1s are given to me. These are the x1s, the y1s are the data points you were given. And so now what's unknown here is the beta naught and beta 1 are the unknowns. And what do we have here? So we have two unknowns, or two variables, and we have n equations. So this gives me a n by 2 system. Okay? And of course this will be inconsistent because what I'm asking for is that all of these points lie on a line, and we just saw in this example that they don't lie on a line, so there's no way to simultaneously satisfy these n equations. So what we want is the best fit. So in general, these points, this system, I'll say, is inconsistent So we want to find your least square solution. Okay. So let me just maybe just to encode this in language that we know, right? So the system encoded as a matrix here would of course be, well, what would it be? It would be 1 x1, 1 x2, dot, 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 1 xn times the unknown, which is beta naught, beta 1, equals the right-hand side, which is y1 through yn. So just to, you can see this on one screen, I'm just taking this system and encoding it in the usual way as a matrix times, so you can think of this as A equals A, beta equals y, the vector on the right-hand side. So let's do an example. Let's say we're given data points, 2, 1, 5, 2, 7, 3, 8, 3. So let me try to actually plot this. So this is, let's see, 2, 4, 6, 8. And 1, 2, 3, not quite to scale. So 2, 1 is given, 5, 2 is given, 7, 3 is given, and 8, 3 is given. So notice again, this is not going to give you a line because, if there was a line, it would have to be horizontal given these two, but it's not because I've got some other heights here. Okay, so what's the system here? We're going to have a 4x2 system. And again, let me just go back to my cheat sheet here to tell me what it looks like, right? So in this case, it's always going to look like 1, the matrix is going to be 1 x1, 1 x2, up to 1 xn. So it's going to be 1, 2, 1, 5, 1, 7, 1, 8. So these are the x coordinates of these data points, times the vector b naught, b1 equals the right-hand side, which are the y values, right? So again, going back to my system here, the right-hand side is the y values of the given points, 1, 2, 3, 3. Okay, so this is the system I'm interested in. It's not going to be consistent, like I said. So, you can check that this is, if you augment this coefficient matrix with 1, 2, 3, 3, you'll see that this is not going to have a solution. So what we want to look for is the least squares. And let me give this a name. So, sorry, if this was A and this was the vector B, I guess, so just to match our old notation, we want to solve ATAX equals ATB, right? So what is ATA? So this is something we've already done, but let's go through the calculation here. ATA is 1, 1, 1, 1, 2, 5, 7, 8. That's the transpose of A. Times A itself, which is 1, 2, 1, 5, 1, 7, 1, 8. And what you get here is, let's see, so the first, it's a 2x2 matrix. The first, the entry in the first row, first column is 1 plus 1 plus 1 plus 1 is 4. And I've got 2 plus 5 plus 7 plus 8, which is 22. 22, and this is 142. What else do we need? We need ATB, which is 1, 1, 1, 1, 2, 5, 7, 8, times the vector B, which is 1, 2, 3, 3. This will give you, it turns out, 9, 1 plus 2 plus 3 plus 3, 9, and then 57. So we solve the little 2x2 system here, 4, 22, 22, 142, augmented with 957. I'll spare you the details here. This turns out to be, well, it's consistent, of course, and it gives you the solution 2/7, 5/14. Okay, so again, just the usual row reduction here. I get the reduced row echelon form given by this, which is telling me that, now don't forget what these were. What were the variables? The variables were the beta naught and the beta 1, where, of course, right, what was beta naught? That was like the y-intercept, if you like. Beta 1 was the slope of this line. So just to remember that this is the line that I'm going for. Beta naught is what we usually call the y-intercept. Beta 1 is the slope. This is now telling me that beta naught is 2/7. beta 1 is 5/14. So what this is telling me is that the line that I want is y equals 2/7 plus 5/14 x. And let's see, does that make sense? I don't know if you can quite see my diagram here, but so this is telling me that it's a slope that's around 1/3 and a y-intercept that's around also, I guess, 1/3. And that makes sense, right? I'm expecting a positive slope here, and it looks like, something like that would be the best fit line. Now, just briefly, maybe I'll mention that, maybe I'll just mention this with this picture here. I mentioned this before. What are we actually minimizing? So it turns out that when I get this best fit line, what I'm minimizing are what are called the residuals, which are the distance between the data points and that line. So maybe I do need a new picture here. So this best fit line, or least squares, line, minimizes what are usually called the residuals. Do I have a notation for that? I don't think so. So the residuals given by, so if your least squares line was y equals beta naught plus beta 1x, then this will minimize y of xi minus yi. So what do I mean by that? Well, let me just maybe just do two examples. Well, I guess I need 3 points to make it look interesting here. But if these were my data points, this was x1, x2, x3, then of course, well, there's a y coordinate, y1, this is x2, y2, this is x3, y3, and this is the line that I've gotten by my least square solution. This residual is what I'm trying to draw here, this, I guess the length of this value here. So these numbers here are the residuals, and the least squares line that I've come up with is the line among all lines that has this value the smallest. So I can take this distance plus this distance plus this distance, and among all the lines in the plane, this line that I've come up with will minimize that value, the sum of those. And let me just end this with, so you can use this. For other, curves, not just lines, e.g. if y was beta naught plus beta 1x plus beta 2x squared, so this was, a quadratic or a parabola. So if you now went back to my, original setup with the 4 data points, I could actually ask for a parabola that goes through these 4 points. And what you're going to have here, if you assume they lie in a parabola, this would give us instead of a 2 by n system, this would be a 3 by n system, where it would look like, 1, x1, x2, 1, sorry, this would be x1 squared, of course. And this would be 1 x2 x2 squared dot 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 1 xn xn squared. And this would be multiplied by 3 things now, because I have 3 variables, the beta naught, beta 1, and beta 2. And then this would equal the right-hand side, which is given by the y values. And of course, this is the data point, in case n equals 4, you have 4 data points. Then the x1, y1, x2, y2, x3, y3, x4, y4 would be the things that you plug in here. The unknowns, again, are your 3 coefficients for the parabola, and you do the same thing. So we'll probably discuss this in a worksheet setting, and I'll see you next time.